to our seminar. So today we have a talk by our great colleague and collaborator, Claudio Campagnari. He's professor at UC Santa Barbara. He seemed to be everywhere during his career, right? He participated in top discovery, then he was in Babar. Now he participated in the Higgs discovery. Now he's looking at new physics. He's been building trackers, and now we're building together immune systems. Right? Trying to anyway. So welcome, and so Claudio will talk about searches for supersymmetry.
So it was a great pleasure to be invited here. I have so many friends here, so it's wonderful. When I was invited to come here, I asked the organizers whether they wanted me to give a general talk, because these experiments like CMS produce a ton of interesting results, or rather focus on something very specific. And they told me that they would prefer me to focus on something more specific, which I actually also prefer. So I'm going to take one particular search at CMS and show you some of how it works, including some of the dirty laundry. And I think that this is going to be particularly useful for students and postdocs at CMS just to see what it really is. So here's the outline. So I will motivate why we're searching for the top squarks or the stops, talk about the production and decay. I will talk in a lot of detail about the searching the electron plus jets mode. And then I will point out the limitations and the conclusions and the prospects. So this is going to be the most minimalistic SUSY slide you'll ever see in your life. I don't want to talk about SUSY. You've heard it a million times. SUSY has some good things, some bad things. But what I want to say is why we are looking for the top score. What happened in the early days of CMS, it became clear that the most generic SUSY models that many people expected would just pop up in the first 20 minutes of running were just not there. Okay, and so well, what's the solution? It's the usual solutions that people invoke. The masses of these particles are higher than you expect, and you can't quite reach them, and take more data, go to a more energetic machine, and look again. That's the usual thing. But the stop quirk is special, and so the stop quickly became the flavor du jour at CERN. If you walked to the CERN cafeteria in early 2011, everybody was talking about stop. Okay, so why stop? Well, one of the things that supersymmetry does is that it solves the hierarchy problem, the naturalness problem, the standard model, which consists of the fact that in the standard model, the Higgs mass automatically gets corrections of the order of the ultraviolet cutoff scale, which could be the Planck mass or the grand unification scale. So a huge scale for the 10 to the 15 or 10 to the 19 GeV. But we know that the mass of the Higgs is about 100 GeV. So there are these enormous radiated corrections, and one of the things that SUSY does is that with the stop in there, in this kind of loops, it cancels this term exactly, and it keeps the mass of the Higgs low. But the cancellation is not perfect. Here there's a term like the top mass, and here's the term like it goes like the square of the stop. The square of the top mass, the square of the stop mass. So if the stop mass becomes too large, then this cancellation still doesn't work. So in order, if you want SUSY to be the solutions to this puzzle, the stops has to be light. It has to be, depending on how you see it, how you look at it, of the order of 500 GeV to 1 TeV, and this is something. This is in the range of masses that can be accessed with the current data. So if you want to, so that's why everybody started going and looking for stops, including me. So so if you want to look for stops, how it gets produced? It gets produced in pairs. It gets produced in the cascade decays of gluinos, for example, or maybe even cascade decays of the heavier partner of the stops. There are actually two stops. There's the stop 1 and the stop 2. Why there are two? Because the top quark has 2 degrees of freedom, left-handed and right-handed. So in supersymmetry, you have to have two partners. One is the part of the left-handed, one is the part of the right-handed. And the T1 and the T2 are some linear combinations. The T1 is the lighter one, and the T2 is the heavier one. So you can make it in a cascade. So you can make it in cascade, or you can make it directly. And so what we are going to concentrate today is on the pair production, the straight production of a pair of stop anti-stop, which get made through gluon fusion. Okay, so now we know how it's produced. Then we have to figure out how it decays, and that's model dependent. It can decay into a top and an LSP, a neutralino. It can decay into a B and a chargino, and then the chargino decays into a W and an LSP. The top you can have this decay, but the top can be off shell. If it's light, it can decay into charge. But these are the main decay modes for stop masses that are above 100, 150 GeV. And so these are the modes that we are concentrating on. Okay, so what are the decay modes? So these are the two decay modes that we look at. Stop goes to top LSP, and stop goes to B chargino. So they call that the top neutralino mode, and this is the B chargino mode. But then the top decays into BW, and the chargino decays in WLSP. Now, if you look at the final state particles, you have a B, W, LSP, LSP, WB, B, W, LSP, B, W, LSP. So the final state particles are actually the same, so it's natural to look for them together. So, but now if you look at this picture, you see that this stop pair production looks just like TT bar production, but there, in addition, you have two LSPs. So stop pair, looking for stop pairs means looking for TT bar production plus MET. Okay, where the missing ET comes to the neutralinos. And so, since the signal is TT bar plus MET, well, the background is stop, it's TT bar. And of course, then you have other smaller contributions that come in and you have to account for. So you do a TT bar analysis, and TT bar analysis are done always in three channels: 0 leptons, 1 lepton, or 2 leptons. And so we are going to I'm going to show you the 1 lepton analysis, which was published last year. Okay, so what is the challenge? The challenge is that the TT bar cross section is enormous compared with the stop pair production cross section. This is a plot of the stop pair production cross section versus the stop mass, that's the red curve. Of course, it falls with energy, with mass, and this is the TT bar cross section. So the TT bar cross section is several orders of magnitude above the stop pair cross section, so you have to beat it down. This is the number of events that are produced in the CMS, in 20 inverse femtobarn CMS, which is about the size of our data set. And so you see that if you have a production of 100 events, 700 GeV stop mass correspond to 100 events produced. Then you put in acceptances, branching ratios, and whatnot, and it sort of tells you that you cannot go much farther than 700, 800 GeV maybe, okay? But the challenge is that this cross-section here, TT bar, is much, much larger, and so you have to fight it, and you have to kill it. Okay, so we were sitting with some colleagues in the cafeteria at CERN, and we decided, okay, let's do this. And so we thought about, what do we do? Well, the obvious thing is that in TT bar plus one lepton, so semi-leptonic TT bar, the missing ET is from neutrinos. So the transverse mass of the lepton-neutrino pair is bound by the MW. In signal events, the missing ET is from the neutrino from W decay and from two LSPs. So the transverse mass can easily extend past MW. All right, so one of my colleagues told me, so this is what it would look like. This would be the TT bar, and the signal will look like this. You look over here, and you look for the stop. And one of my colleagues told me that it was going to be a cakewalk, and no problem. You know, a couple of weeks we'll whip it up, we would write it up, and that's it, done. Well, not so fast. This is the transverse mass for a typical TT bar selection, where you select lepton, missing ET, and 4 jets. And here's the purple is the 1 lepton top. Okay, so this is the semi-leptonic TT bar decays. And yes, they die at about 100 GeV or so. But there is also a contribution from TT bar dileptons that keeps going forever. Okay? So the tail of TT bar, where you're looking for the signal, is dominated by TT bar dileptons. So the first thing you have to do is work really, really hard to eliminate events that have a second lepton. So you go and use all the tricks in the book to eliminate them, and you reduce them by a big factor, but they're still there. And I will show this compared with some stop signals in a minute. So the first thing you have to do is you have to do an aggressive second lepton veto to remove TT bar dileptons as much as possible. So in order to go further, you have to use some kinematic information. And so we spent quite some time investigating all kinds of possibilities. So let me show you some possibilities. The first one, actually, one of the most useful ones was actually suggested by these guys, these theorists from UC Davis. And what is it? So here's a T, it's called MT2W. And it's a variable against dileptons. So this is top TT bar, it goes into a B and a W. And you have missing ET from this guy. And you miss this guy. You don't see it. So everything that is in red is a missing particle. So the missing ET comes from this guys here and from this guy. So MT2W is the minimum mother mass, meaning the mass of the particle, the particle that pair decays, compatible with all PT and invariant mass constraints. So invariant mass constraints are that the transverse momentum of this guy plus the transverse momentum of that guy is the missing ET. This guy has a mass of 0. These guys have the mass of the W. So it's like you try all possible combinations, you find the minimum mass, and you plot it. Okay, this is a very cool idea, turns out. And this is what it looks like. This is in simulation. This is the plot of this variable MT2W. This is all still Monte Carlo. This is the background, the TT bar background. The red is the one lepton, the TT bar to one lepton. The blue is the dilepton. And you see that it dies at the top mass pretty well. And now this is a simulation of a particular model with a mass of the stop of 650 GeV, mass of the LSP of 50 GeV, but it's boosted up by a factor of 100 so that you can see it. It's still a tiny little signal. So this is one variable. And then there are other variables. Turns out that many signal events look like this. The T and the T bar are on one side and the LSPs are on the other side. Not all of them, but many of them. But most background events look like this. The T is on one side, the TT bar is on the other side, and the ET misses somewhere. And so the fraction of hadronic energy in the same hemisphere as the MET is a useful variable. So this is a plot. This is the background. So this is the fraction of MET in the same, the fraction of hadronic energy in the same hemisphere as the missing ET. And you see that for the signal, there are quite a few events with very little hadronic energy over here. Whereas for the background, it looks quite different, so that's another kinematical variable.
So is this the same thing as just saying that PT of the TT bar system?
Yes. Yes.
So that would be an equivalent variable.
It's a very correlated variable. So here's another one. As I said, most background events look like this. You know, you can scan the events that pass in Monte Carlo that pass. They look like this. So you say, oh well, okay, global event shapes, sphericity, thrust, whatever. Turned out that actually the best separation is if you calculate the minimum opening angle between the jet and between the MET and one of the two leading jets, and this is what you get. So again, some separation, not perfect, but you get some separation.
Claudio, when you say jet 1, jet 2, it doesn't matter.
Doesn't matter. Then there is the ace. What people think is the ace in the hole. In the hole, well, in this decay mode, there's a hadronic. Here there's a hadronic top decay, right? So let's reconstruct the top mass using the jets. It looks wonderful, and it works at some level, not perfectly. So what we do is we build a chi-square to the 3-jet hadronic top hypothesis. and it looks like this. So this is the background, and this is some signal. There is some discrimination. It's not great. And the reason why the discrimination is not great is because jet combinatorics and missing jets and the usual stuff. Then if you look at the B Chargino mode, the B quark properties are clearly important because it's different whether the B quarks come from the top decay in the background or directly from the stop decay as over here. So for example, this is the PT of the B quark. And this is some separation between the B quark and the lepton. So those are other kinematical variables. And so we have all these kinematical variables, and we have to put them together. And so here is how it works. The signal selection is you start with a simple lepton plus jet selection. You kill as many TT bar dileptons as you possibly can. And then you use the kinematical variables to reduce the backgrounds. And we do this in two different ways. We do this in a multivariate way, where we throw everything into a boosted decision tree. And we also do it in a cut and count way, where we just put 3 or 4 cuts on variables. And we have different signal regions to cover as much phase space as possible, because you have to cover all the phase space, and the kinematical properties change from point to point in phase space. The background comes from Monte Carlo, and we calibrate and correct the Monte Carlo with control regions, as I will show you some example in a second. So the pre-selection is simple. One isolated electron muon, 30 GeV, 4 jets of 30 GeV, at least one of them is B-tag, a good amount of missing ET, and a second lepton veto. We want to kill dileptons, so we need a second lepton veto. The dilepton veto is pretty aggressive. We actually veto isolated tracks, not leptons, down to PT of 10 GeV. This also catches some taus, which is a good thing. If the track happens to smell like a lepton, we go down to 5 GeV, and we even open up the isolation requirements even further. And then we try to identify hadronic tau candidates up to from PT greater than 20 GeV, and this catches some of the multi-prone tau decays. So you have to throw the kitchen sink at this dilepton background to get rid of it as much as possible. So then, as I said, we have two selections. One is straight cuts, and one is a multivariate selection, which is a boosted, turns out to be a boosted decision tree. The multivariate has the ultimate sensitivity, okay? The cut and count is arguably more robust, but there's something more important about the cut and count. The cut and count is less sensitive to the details of the model, and I will come back to that later on. So what we do, in effect, is we do both analyses in parallel, okay? From the same baseline, we push a multivariate analysis and a cut and count analysis all at the same time. So these are some of the kinematical quantities, we demonstrate. The first thing you have to do, you have to demonstrate that they're well understood. So we look at the pre-selection, which is the selection of lepton plus 4 jets, and we look at various variables. So this is the transverse mass. I told you that it has a tail, which is dominated by the light blue, which is dileptons. This is a signal boosted up by a factor of 1,000. This is the missing ET. Again, this is the same signal boosted up by a factor of 1,000, but you see data in Monte Carlo agree, so we understand this sample. This is this MT2W that I was telling you about, also boosted up. And this is the hadronic top chi-square, the ratio of the hadronic energy in the hemisphere of the missing ET to the total, the delta phi angle between the missing ET and the jets. This is, you can't read it here, but this is the PT of the B quark. This is the opening, the delta R between the B quark and the lepton, and this is the PT of the lepton. And they're all pretty well modeled before we start doing things to them, but you see that the background is enormous. Okay. So it gets more complicated because, as I said, the cross section and the properties of the signal vary widely as you change the stop mass, and so you have to introduce different signal regions. Okay. And so you have to introduce a set of cuts that are targeted to this corner of phase space, a set of cuts that are targeted to this other corner of phase space. So it's not just one analysis, it's a whole bunch of analysis. So how does it work? So if you take the top neutralino mode, for example, here's the plot of the transverse of the stop mass versus the LSP mass. The kinematics is driven by this quantity, the energy, the mass difference between the stop and the neutralino. And so we define different regions here of phase space where we train different boosted decision trees. So we train 5 different boosted decision trees for this mode. For the charging it's more complicated because not only because you have another degree of freedom, which is so here's the stop. This is a mass spectrum. The stop is heavy, is the heaviest. The LSP is the lightest, and then you don't know what the chargino is. You can put it here, you can put it here, you can put it there. So we take these 3 types, these 3 spectra, and we define again regions where we train the boosted decision trees. So we end up training 11 boosted decision trees. And now and then we have the cut base, the cut and count analysis, where we cut on some variables and we apply.
So in the chargino case, the delta n, okay, it's a chargino minus LSP.
Yes. So this summarizes which variable goes in which BDT and what the cuts are on the cut and count. It's detail is not very interesting. But here's an interesting thing. We end up with 18 BDT and 16 cut and count signal regions that we have to carry through with us in this cakewalk.
So it's basically 18 separate analyses, right?
34.
Well, yeah.
It's a cakewalk. And then we put a cut on transverse mask, which is common to all of the analysis. So, okay, so we decide how to select the signal. So now let's talk about the background determination, which is the most important part of the analysis, in some sense. So what we do is define control region to test the Monte Carlo modeling of all the individual variables. For example, we have a control region where we veto B quarks, and this is enriched in W plus jets. And we have a control region with a second well-identified lepton or an isolated track, and this is enriched in TT bar dileptons. Okay? So an important thing is the modeling of initial state radiation, because this is a dilepton decay of the TT bar. Okay? If you count the jets, there are only 2 jets, but our signal has 4 jets. So in order to model the signal, this background with the Monte Carlo, you have to check that you know how to model TT bar plus 2 jets, and 3 jets, and 4 jets. Because you need 2 jets from initial state radiation to pass the selection. So you have to be careful there. And so this is the jet multiplicity that we measure in the control sample of TT bar to dileptons. This is data divided by Monte Carlo. And so this is 1 jet, 2 jet, 3 jet, 4 jet, 5 jet. Up to 6 jets, we are within 10% of the background of the Monte Carlo. So the Monte Carlo is doing an extraordinarily good job to model the additional jets in TT bar events. So it works pretty well. This is where the ISR jets live. One ISR jets, 2 ISR jets, 3, 4. So here's some checks that we do. So here's the flow chart of the analysis. So we do a pre-selection, and then we check data Monte Carlo agreement of all the kinematic variables, and if there are kinematic variables that don't agree, we worry about it. We try to fix it, and if we cannot fix it, we use some other kinematic variable. Then we calculate the boosted decision tree, all 16 of them. Then we check the BDT output on the background dominated region. And then we cut on the BDT, we apply a transverse mask cut, and this is the final selection. This is how we check the TT bar lepton plus jets, because the pre-selection is dominated by lepton plus jets. The dilepton background, well, we do a very similar thing. We do a pre-selection with the second lepton veto inverted. So these are the ones that that look like they have a second lepton beat. And we do the exact same thing. Check the kinematic variable, calculate the BDT, check the output, and then we cut on the BDT, we apply the cut, and we compare data in Monte Carlo with the final selection for background events.
So somehow we're combining PDTs, or these are just, you know, like
Multiple.
analysis?
Multiple. And for the W plus jets, we do the same thing, but starting with a B-Vito pre-selection. Okay? So this is repeated for 18 BDT and 16 cut and count 34 times. So let me just show you some example of these checks to give you a feeling for what we're doing. So this is the lepton plus jets. We check the BDT output in a background-dominated region. So this is the BDT output. This is the Monte Carlo. This is the data. This is data divided by Monte Carlo. Agrees very well. And this is what one of these models would contribute, scaled up by a factor of 30. Okay. And so this is a BDT1 in region 1, whatever that means. And this is BDT4 in region 4. Same thing, BDT, and here's where the background, here's where the
Claudio, you
system.
didn't use MD to the.
Huh?
You didn't use MD to the.
It's in the BDT.
Maybe, okay.
It's in the BDT. This is the dilepton background. So here's an example, check of the kinematical variable. So this is the MT2W checked in the dilepton sample. Okay?
So
This
these
is
are
the
control regions?
what?
So these are control regions?
This is the same as the pre-selection for lepton plus jets, but we require that there is a second lepton as well.
Okay, so that's why you're not seeing any place where a signal could be, but in the previous one you did?
Right. Well, technically there is some signal, but it's down by another 2 orders of magnitude. So.
So that, all right, so once it's by 100, you're not worried?
Yeah.
Okay.
This is the BDT output checked on dilepton events. So, and this is the BDT output checked on dilepton events. Then we cut on the BDT. So this is the final thing for the dileptons. We cut on the BDT. The cut is here, turns out. And we looked at the transverse mass variable, and the Monte Carlo does a very good job understanding of reproducing the transverse mass variable. There's one check that does not look so great. So this is the dirty laundry. We look at W plus jets, and we select the events with a B veto. So this is W plus 4 jets or more, and we look at the transverse mass, and it doesn't look so great. Okay, it's off by about 20%. When we started the analysis, it was off by a factor of 2.5. So we worked a lot to fix all sorts of problems. So if you guys work on CMS, you're told that the CMS Monte Carlo is perfect and the missing interior resolution is perfectly understood. Not really. Okay, it's not true. Okay. So
Is this true in E's and Mu's?
yeah. It's true in E's and Mu's. It's true in at this level of the selection, at further levels of the selection. It's sort of constant. Okay. So this is an issue with the missing interior resolution, which affects the transverse mass measured in W plus 2 plus jets. And you can correct it by a scale factor for the 20%, 1.2. So that's relatively painless. What's painful is that will affect the TT bar lepton plus jets also. Okay? And what's painful is that transferring this measurement to lepton plus jets is highly non-straightforward. For example, in W plus jets, a lot of the events in the tail of transverse mass are actually there for a good reason, meaning that you made a W that is way off shell. In TT bar, it doesn't happen so much because the W cannot be, the W mass, the off-shell W mass cannot be greater than 170 G. So the admixture of the various components, real W stars versus screw-ups in missing energy, are very different in W plus jets and TT bar. And so you have to work really hard to transfer one into the other, and this ends up being the main source of systematics. At some point, we started out with a scale factor of 2. We got down to 1.2. We ran out of ideas. We punted. assigned a systematic and moved on. So these are systematics on the background. We do it BDT by BDT. I don't want to go into details, but I'm going to show you that we have to fill out tables and tables and tables of numbers. But let me just point out some interesting features. These are the uncertainties due to the missing ET resolution. Okay, and they can be high. They can cause as much as a 30% uncertainty on the background prediction.
Claudio, these are the different regions are correlated, right? Then you add the final.
No, because when we go to the end, we either for each point in space, we pick the one that is the BDT that is supposed to be the best for that point and ignore all of the others. If we are setting limits, if we're making a discovery, then everything else is changed. Okay. These are the dilepton background is the main background, and its uncertainty is set by the statistics of the control regions, and it goes between 4 and 14%, depending on how tight you're cutting. In some cases, Monte Carlo statistics comes in, so these are Monte Carlo statistics issues. There are also some weird events that can sneak into here, like TT bar W production, which Slava is working on measuring now. Those are rare processes, but they can enter this selection. We assign them a generous 50% uncertainty, and it gets reflected in uncertainties that are completely negligible for some BDTs and up to 16% for some other BDTs.
Is TT bar Z more visible or not?
It's mostly TT bar W because of the missing ET. Yeah.
Well, Z. Well, I guess
Oh,
Z
there's
is
a
not
TT bar
posted.
Z neutrino. It's also in there. So it's a TT bar Z where the Z goes to neutrinos. It's probably the worst, which is the one you're supposed to be measuring.
Yeah.
What about TT bar Higgs? You throw that in there also?
We throw that in also. So this is the bottom line. The total uncertainties will go between 13 and 40% on the background. And these are the expectation. Again, I'm taking one sample table for the BDT for the top neutralino. So here's a loose selection, which is tailored to light stop. So we expect 760 events, and the light stop would contribute about 300.
What are you optimizing for? Signal over square root of background or confidence limit? Or?
Signal over square root of signal plus background. No, signal over square root of background plus systematic error guessed.
Okay, so you're not using the production cross section in there. It normalizes out. Okay.
This is so this is a BDT that is aimed at the high mass stops, and you see this BDT is completely useless for the high mass stops. 760 events expected from background, 12 expected for high mass stop. But this is a tight BDT where you only expect 3 events, and high mass stop will give you 4.3. So you're starting to get some sensitivity across a broad mass range by having this spectrum of requirements. So this is the results. You can compare the total number of events down here in the various BDTs with the prediction of the background, and you don't see any excess anywhere.
You got a deficit in 6 out of 6.
Yes, we do, and we think they're correlated, and we think they're correlated because this guy here, this arrow here, is correlated. It's a systematic error, which looks like, it looks to me, if I had to put my money, we say it's between here and here, and we take we take the central value to be the middle, and probably the real value is somewhat lower than the middle.
So a lot of these events could all be the same.
Yeah, some of them are the same.
So in fact, the right 5 could all be in the left 1.
It could, not all of them, in principle they could be. It's different analysis. So here's some examples of what comes out of it. So this is a BDT distribution after you cut on the transverse mass for the loose BDT. Okay, So here's how this is what the BDT looks like. This is what this point would look like. Now this point is not scaled now. This is just absolutely normalized. And you see that if we had this, if nature gave us a stop 250 and an LSP of 50, we would have seen it. This is and this is the other view where, so this was the BDT with a cation transverse mass, and this is the transverse mass with a cation BDT. So you would have seen all of these events.
Claudio,
Yeah.
the shape of the BDT,
Yeah.
and the state function functions kind of
Yes, it's because when some variables come in and some variables go out. We don't fully understand it, but it has something to do with. Let's see, what was this one?
exactly 0.2.
Yeah, I don't know. It's exactly point on the beginning. But if you look at these BDTs coming out, in general they go like this. And the amazing thing is that the data also does this. Yeah. When we first saw it, we thought that the BDT was drunk, but that's what it did.
So are they in analysis now?
Yeah, some of them are.
No, this is sort of branches, right?
Yeah.
One piece, another piece.
This is another one. Again, the BDT. This is for a high mass stop. The BDT with a cut at 120 GeV, and then the transverse mass with a cut on the BDT. Okay, so then you don't see anything, so you don't see a signal, so you put a limit. So here's the top neutralino mode. This is the neutralino or the LSP mass. This is the stop mass. At each point here, you figure out what is the BDT that is the most sensitive, and you use that point, that BDT, to set the limit on the cross section. So this color code here is the upper limit on the cross section, and then the lines tell you the region that has been excluded, where the upper limit of the cross section is above the theoretical cross section. Okay, so we get up to something like 650 GeV in stop mass when the LSP is when the neutralino is light. This region here is where the top is off shell, and this region here is where basically the stop, the difference of mass between the stop and the LSP is the top mass. So there's a hole here in the sensitivity, and I will come back to this hole in sensitivity because it's interesting. Okay, so these are the same limits for the Chargino mode, and I remember there are 3 spectra that we do, and again, typically 650 GeV or so. You may wonder, what does the BDT buy you with respect to the cation count? This is for the top Chargino mode. This is the BDT exclusion region, and this is the cation count region exclusion. Okay, so it buys you. The limit goes from 650 here to 620, 600. It buys you not very much. Okay, which is an important lesson. And the reason why it doesn't buy you very much is because the cross section is falling really fast. So there is a zeolactone. So this was one lepton. You can also do a search in zeoleptons, and the dedicated search from CMS is not out yet, but there is a generic search, and this is what it looks like. It extends the mass reach a little bit, and a dedicated search is being finalized. So now let's talk about some funny dirty laundry. So first of all, the polarization in stop decays. When the stop decays, the top can be polarized. Okay, and the polarization of the top depends on a complicated. It's a complicated function of the mixing in the stop sector and the mixing in the LSP sector. It's easy to understand. For example, it looks very mysterious, but it's easy to understand because imagine that let's pick this one. Imagine that the LSP was a Wino. Well, the Wino only coupled to the left-handed part. So the right-handed stop will never decay to the LSP, and the left-handed stop will only decay to the left-handed LSP. So it gets complicated, but the bottom line is that the polarization of the top is a complicated function of SUSY parameters. And it matters because in the top rest frame, the direction of which the in the W rest frame, or in the top rest frame, the direction in which the electron goes. So this is the direction of motion of the top, and this is the direction of motion of the lepton. In the rest frame, the leptons tend to be thrown forward for right-handed polarization, backward for left-handed polarization. And therefore, as a result, the transverse mass distribution looks very different for right polarization and left polarization. And the limits change by about 20 or 30 GeV, depending on what polarization assumptions you make. Now, what's interesting is that the reason we discovered this is because the first version of the analysis, we looked pretty bad compared to Atlas. And so we had to go and look and figure out, and it turned out that they had picked right-handed polarization, which gave them the best limit, completely by accident of their Monte Carlo. They weren't even thinking, and we had picked unpolarized because who knows what it is. In the Chargino mode, it's even more complicated because you have 4 different types of polarizations, and you see that your results can vary quite a bit. So this is actually a lesson for students and postdocs on CMS. When you do this analysis, you're sent by your review committee to look at all sorts of details, and all of those details are completely irrelevant on the scale of things like this, just for fun. Then what about the mixed channel? So we looked at 100% decays like this, or 100% decays like this, but we have 2 top quarks. So imagine that the branching ratio is not 2 stop quarks. Imagine the branching ratio is not 100%. So sometimes it's going to go like this, and sometimes it's going to go like this. But then what? In fact, this is what you expect. Some branching ratio here and some branching ratio there. So this is why the cut and count analysis is important, because it's generic enough that it probably should have about the same sensitivity even when you mix up the decays. It's not specializing on some corner of phase space like the boosted decision tree. But there is a very important loophole, because imagine that you have a spectrum like this, which actually is the spectrum that is favored in supersymmetry, with the Chargino and the Neutralino maybe 1 GeV away from each other. Well, it turns out that our analysis has 0 sensitivity to this, because as soon as you get this kind of decay, the kind of decay chain, the particles that get emitted in the standard model particle here, get emitted in this decay, are too soft to be seen, so there are not enough jets, and so we have 0 sensitivity. And this is how the sensitivity degrades very quickly with the branching ratio. The red one here is 50% branching ratio. Kind of sobering. So what we're doing now is combine with some low jet multiplicity full hadronic analysis, and I think this will close most of this loophole, but we don't have results on that. Then let's talk about this whole insensitivity here, which is interesting, and it can be addressed in 3 ways: cascade decays, top cross-section constraints, and boosted events. So in cascade decay, so here's a cascade decay with the Gruino, goes to top and stop, and then the stop goes to top LSP. And this is the mass of the Gruino that is excluded in this analysis. And the bottom line is that this hole here is pretty much closed as long as the Gruino is below about 1 TeV. Okay. You can also have this cascade decay where the stop 2 goes to the stop 1, spitting out a Higgs. So now we find the Higgses and stops in the same events. Very exciting. We look at that. So this is analysis where you pick this decay here to be such that the mass of the stop minus the mass of the LSP is the top mass, and basically the hole is closed if the stop 2 mass is below 600 GeV or so. But it's not completely closed. Now here's an interesting one. So if you're sitting here, the top and the stop would have the same mass. And this would increase the cross-section by about 15%. And the theory on the cross-section is 6%. The experiment on the cross-section is 4%. So you can get some information there. But there's a problem. So here's a plot that would show something like this. So here's the mass of the top, and this is the measurement. Here's the cross-section for TT bar pair production from theory, and here's the cross-section measured by the experiments, which depends also on the top mass very slightly. And this is an old plot, so it's not the latest one. And you can look for consistency between these three bands to exclude this possibility here. But there's a problem, and this is a Q problem. If there was a stop here, it would also bias the top mass measurement in an unknown way. And so maybe this top mass measurement that comes out of the Tevatron or out of CMS and Atlas would actually be wrong. Maybe it should be over here or over there. And so you cannot. So the situation is really not clear. Okay. Here's another possibility. You can design an event selection with events recording against an ISR jet. So if you get a boost from the ISR, the momentum of the LSP, which in this region the LSP is at rest. It doesn't give you any missing ET, almost at rest. It doesn't give you any missing ET, and that's why you have no sensitivity. But now imagine that you select events where the whole stop pairs are boosted against an ISR jet. And this, we're working on this, and it looks like we can get 2 sigma sensitivity, and we're combining with other with other modes. Looks like we can get 3 sigma sensitivity in this region. So this is something we're working on right now. It would be nice. It would be nice to close off as much as possible as this whole. Okay, so let me conclude. There are no signs of stop quarks at CMS. I didn't show anything about from Atlas, but it's pretty similar. These null searches are beginning to be a serious challenge to natural SUSY. There are loopholes that remain, even for relatively light top squarks, and some of them are being addressed now to try to close them. And with a new run at higher energy, one should be able to extend the sensitivity, at least in terms of exclusion, to above 1 TeV, and that would really be a strong challenge to this naturalness concept. Thank you.
Questions?
Yeah, maybe.
So it was interesting that what you found was that the boosted decision trees are better than the cut and count, which is not terribly surprising. But in some sense, what you've got are, what was it, 16 cut and count, 18 cut and count?
Yeah, something like that.
So what if you had done like 1 cut and count or 2 cut and count instead of a whole bunch?
Yeah.
Would you have lost a lot? Because in some sense, what we're seeing is that you now have more small empty spaces than the area in the empty spaces is now looking more than the amount that you could sort of push into.
Yeah, look, the issue is that you have 2 different modes, and so the cut and count for this mode and this mode is different because here, so in this decay you go stop to Chargino and there's a big quark here. And in this decay you go stop to top, and so the big quarks are different. So it's natural to have 2 sets of cuts, one optimized for this and one optimized for that.
Well, those are different final states.
Yeah.
But in
So
some sense, if you had 1 per final state.
So in the original, in the first version of this analysis, I went out to some conferences. We had, I think, only 2 of them, and it wasn't 2 or 3, and it wasn't very sensitive. I think we went too far the other way. If you ask my opinion now, but we could have gotten away with maybe 60%, 2/3 or half of them. But at some point, this becomes like a machine. You just run it, and it's just that you have to make a gazillion plots and check every single plot, which is tedious, but it's doable. I mean, it sounds terrible to have 34 signal regions, but it's not so bad. It turns out.
I'm not worried about the number going up. The problem is as the number goes up, you become more and more tuned. So you become more and more reliant on the details of what it is you were
Yeah, the
looking for.
BDT is definitely tuned. The current counts are not very
Yeah, but-
tuned. Basically, what happens, the difference between current counts, one current count and the next, is that you move the missing ET cut further out. That's the main difference. So it's not so tuned. If you.
But then you
there
can just
go.
do a simple likelihood as a function of,
So, yeah, 150, 200,
Yeah, you could
250.
make this thing as, I don't know, like some sliding cuts or something, it's pretty
No,
much
but
the same, right?
150, 200, 250, 300. We could have probably done 150, 300 and be done with it.
or a simple likelihood. MC
Yeah, we didn't want to do shape analysis because it's, if you do a likelihood, it becomes a shape analysis. And so we wanted to keep it as a cut and count,
Right.
okay? Because a shape analysis brings another set of complications with it.
Other questions?
Yeah.
You showed, you compared your ligand with zero electron channel, but what about two electrons with
Okay.
opposite charge?
So, okay, so first of all, this is a generic, this green one is a generic zero lepton analysis. Well, it says zero lepton and one lepton, but it's a generic zero lepton analysis, which is not tuned to this. It's a standard, missing ET plus jets analysis. It happens to have some sensitivity. There is a tuned analysis that is being developed. It's not ready. We're not doing it. That should be better than this green. It should go some. I think it's going to go something like this. The dileptons have very little sensitivity. They're going to do something like this. They're being worked on right now, but they don't have sensitivity. But what I want to do is I talk to the dilepton people, and they're also going to do an ISR selection here. And when I combine their analysis with our analysis, the dilepton and the single lepton, I think we can take out a bite of this, which is more interesting.
More questions?
What about this loophole part where the top and stop are degenerate? What kind of sensitivity do we have from analysis, like from properties of the decays, either
So
polarization or TT bar gamma?
So
kind of stuff?
one of the key thing is one of the key thing is that you can look at the angular correlation between at the angular correlation between leptons, which is sensitive to the spin in the dileptons, which is sensitive to the spin. The differences are very small. They're there, but they're very small. TT bar gamma, I don't know, why would it be good? The charges are the same, so the couplings are the same.
Yeah, but photon angular correlation with the rest of the stuff.
And that one, I never seen an analysis of that.
In some sense, the TT bar photon might give you some handles on your PT distribution of your TT bar system, which looks like it's a big part of your game. Right? So one of the things that it looked really encouraging there is looking at the PT of the TT bar system. And in some sense, if it's about ISR or FSR, looking at a photon gets you out of the combinatorics problem.
Well,
Plus you
we
measure
have
it
measurements
well.
of the PT of the TT bar system. They have been done, but they're done. Some we did in the context of this analysis because we worried about it. Using dileptons, there are more precise measurements made from fully reconstructed top events. It doesn't work perfectly in Monte Carlo, and so in fact there's a debate going on in the collaboration now on how to correct the Monte Carlo to take that into account, and whether the issue is the PT of the pair or the PT of the individual tops. And I think it's probably a combination. But that kind of stuff is being looked at, and some of it was looked at because of this analysis.
Claudio, in your control regions, you looked at inverted lepton E2, right? But you still need to know that probability to misreconstruct lepton is also
Absolutely.
correct.
That yes.
How did you do that?
Okay, so that is measured,
Because that would be more difficult, presumably.
okay,
right?
so there are two ways that you miss electrons. One way is you miss them if they go outside the acceptance. So for that, we looked at how stable it is under changes in the top Monte Carlo settings, whether the various scales, the various types of Monte Carlo, PTA versus McGrath versus Powering versus MC Adenero. So we have about a list of 8 TT bar Monte Carlo sets that we compare the results and make sure that they're stable. Then there's the technical issue of you're missing them because they're not isolated. Okay, so this is taken from Monte Carlo, and we measure this probability of missing it from Z decays as a function of, and we tracked how the Monte Carlo does that probability of missing them as a function of jet 1 jet, 2 jet, 3 jet, 4 jet, 5 jet, 6 jet, and that is how it's done. And a systematic is associated with that.
Because that, like when we do something that is 1 minus efficiency, right? That
Right.
could potentially give you.
Exactly.
But I saw that you also had a plot that where you did have the contribution from two left TT bar significant. I think it was in one of your.
Yeah, they are all. It's always significant. So, but
No, but I saw that the data was actually pretty closely following the prediction.
Yes, for example, this one.
Yeah.
That's a bottom line distribution for this particular BDT.
So I suppose that basically tells you that you got it right.
Yeah. And this is, we always, instead of looking at, this is hard to see because it's on a log scale, we always want to look at this one.
Any other questions? Well, let's thank our speaker again.